All right, my friends, look who got her splint off. So I'm back. I can do this video for you after all. Section 11.5, I'm going to break into 3 parts. So part 1, and it's going to seem kind of funny to bring it up, but part 1, we're going to do a review of some of the summation formulas from chapter 8. And then we're going to add in part 2. And for part 2, we'll be talking about rectangle approximations, of area. And then if you add what we learned in part 1 and part 2 together, along with a couple things that you've learned in 11.4, you will get part 3, which would be how to find exact area, or finding exact area. Okay, so getting started on part 1 here. Let's review just the summation formulas that you're going to need for this section, okay? So some key summation formulas. Okay, so first one, let's say you have the sum as I goes from 1 to some upper bound n of a constant. So here C is a constant. How do you do that? And so a quick, actually, I think with this one I could illustrate it. You could kind of teach yourself by example if you ever, were needing this but forgot it. So an example could be the sum as I goes from 1 to 9. So here the n value is 9 of 7. If you were to expand this out, you'd have 7 plus 7 plus 7, and so you'd have 9 sevens essentially. And so the answer here would be 63. At least I think that's what 9 times 7 is. Anyway, so in general here, you would just take your upper bound and multiply it by the constant that's here. And that's only if you start at 1, but everything that we'll need today starts at 1 anyway. So it really can be that simple. And so to feel like you're doing well with when we get to part 3, you will want to memorize anything that I put in a bubble here on this lesson. Even though you're doing online learning and all that stuff, you'll still want to do yourself right when it comes to this lesson. Okay, do yourself right. Do right by yourself? I don't know. I'm not sure exactly what I meant by that, but anyway, hopefully you know. Okay. Excuse me, kitty. You gotta move. Okay, the sum as I goes from 1 to n of I. It would be super cool if somebody out there actually remembered that one from back in the day with chapter 8. So this one, if you were to expand it out, it would just be 1 plus 2 plus 3 plus 4 plus 5, and so etc. until you get to your last number here. And so a formula that we learned last time was like a formula for an arithmetic sequence. So what you would do here is you would take the first number, which would be 1, you'd add it to the last number, which would be n, and then you would multiply that by the number of terms, which here would be n, divided by 2. If you write that down and kind of make it look cute, it could look like this. So little memorization bubble for you, and then a little illustration as to how that could be used. So if we had the sum as I goes from 1 to, let's say, 100 of I, if you were to expand this out, long way type deal, term by term expansion. This is sort of what it could look like. The dot, dot, dot has the 4, 5, 6, etc. in there. So you could do this by kind of adding, like we mentioned before, the first and the last term, second to last. You'd keep getting 101. And then you would figure out how many pairs of 101 you'd have. And since you have 100 terms, you'd have half that many pairs that equal 101. So you could basically do 50 times 101. And then you would have gotten the same thing had you used this formula. So your upper bound n is 100 times 100 plus 1 over 2. And so here's your 101, and then here's your 50 right there, okay? Either way, you'd end up with a final answer of 5,050. There we go. Okay. All right, so each time I'm just going to give you the property and then give you an illustration to kind of remind you of what it meant. Because it turns out you can memorize these all day long, but if you don't really feel comfortable with what they're for and what they mean, then it won't do you much good. Okay, property number 3, the sum as I goes from 1 to n of I squared. This one you get, let's say you get 50,000 imaginary bonus points, if you can remember what this one was. This one would be your upper bound n times n plus 1 times 2n plus 1 all over, anybody remember? It's 6. All right, so an example to illustrate this would be the sum as I goes from 1 to, let's say, 5 of I squared. Now I kept that upper bound really low so that we could do this term by term. So if you do this term by term, you just get 1 squared, which is 1, 2 squared, 4, 3 squared, 9, 4 squared, 16, 5 squared, 25. And then you could just add these together. Let's see. And I think you'd end up with 55. Yeah, 55. Okay. So you'd end up with 55. So that's not the point of the lesson, though. That is what you could do if you just did the if in doubt, expanded out way. Another way to get the same answer would be to just use this formula. So the upper bound is 5. So you'd have 5 for n, 5 plus 1, or 6 for n plus 1. 2 times 5 plus 1 is 11, and then over 6, and then the 6's cancel. And you can see you get the same answer with this formula that's in terms of your upper bound as you did by doing if in doubt, expanded out. There we go. Okay, so another little thing for you to memorize here. Okay, fourth one. It's going to be the sum as I goes from 1 to n of I cubed. The formula here, let's see if you remember it, is n squared times the quantity n plus 1 squared all over. Do you remember? 4. Okay, memorize that. And then a quick example illustrating this, let's see if I can fit it in here, would be, I'm going to keep the upper bound low so it's easy to check it with if in doubt, expanded out. So the sum is I goes from 1 to 4 of I cubed. So here your upper bound is a 4. So if we did this by if in doubt, expanded out, you just have 1 cubed or 1, 2 cubed is 8, 3 cubed is 27, and 4 cubed is 64. And then if you add this all up, I think you get 100 even. Or you could use the formula. So if you'd use the formula instead of doing it term by term, you would end up with 4 squared, or 16, 4 plus 1 squared, which is 5 squared, so 25, and then over 4. The 4 and the 16 can cancel, so you're left with 4 times 25, which is 100. Okay, so I'm hoping at this point that I've communicated basically that you need to memorize these 4 formulas for your own personal sanity for what is to come, and that the little illustrations are helping you to feel confident in what you can do with them. Okay, 2 more little summation formulas, and then we'll do a little bit of practice with an example or 2. So just let me get lined up here. There we go. Okay, so some properties of sums. That we will need for this lesson. First one would be the sum as I goes from 1 to n of and I'm going to say a sub I. So this is kind of like f of I right here. Either plus or minus b sub I. And actually, let me take the plus or minus off for right now. It's a little early. But let's just say plus b sub I. So this is kind of like one function of I, and then this is another function of I. So a sub I could be thought of as f of I, and b sub I could be thought of as g of I. So these are just two functions of I, where I is your index. I is the thing that changes. It starts at 1, then goes to 2 to 3, and then it stops at n. So this is review. So here it turns out that you can take the sum as I goes from 1 to n of this function of I, and then the sum as I goes from 1 to n of the second function of I, and add the two results together. So it would look as if sigma kind of distributes over addition. There we go. My math teacher, when I was in high school, would call this property, what did he say? The sum of a sum is the sum of the sums or something. Anyway, I don't know. If that makes sense to you, then awesome. Okay, and then for this one, we could do actually a mini proof of this one. It's easy to prove instead of doing an example. So the proof would be, if you have this sum as I goes from 1 to n of a sub I plus b sub I. And then if you start expanding it out term by term, you'd first plug 1 in for the i's. So you'd have a sub 1 plus b sub 1. Whoops, 1. And then you'd plug in 2 for I, so you'd have a sub 2 plus b sub 2. And then you'd plug in 3 for I, so you'd have a sub 3 plus b sub 3. And you'd keep at it until you finally plug in n, so you'd have a sub n plus b sub n. Well, notice that all I have going on here is a whole bunch of addition, so the parentheses are doing absolutely nothing. And you can use properties of addition, like commutative and associative properties, and reorganize this and still get the same answer. And how would I reorganize it? Well, I would choose to put all the a terms together. So a sub 1 plus a sub 2 plus a sub 3, and then etc. until you stop at a sub n. And then I would choose to put the b terms all together. Like so. And then if you kind of, I think of this as putting Humpty Dumpty back together again. So if you look at this and put it back into sigma notation, what sigma notation would expand out and equal a sub 1 plus a sub 2 plus a sub 3 all the way to a sub n? Well, it would be the sum as I goes from 1 to n of a sub I. And then how about this part? How would you put that back into sigma notation? Well, it would be the sum as I goes from 1 to n of b sub I. There you go. So we just proved it. We did it in general, so it would work for any function rule. And then back to what I kind of preemptively, or prematurely, I guess, said before, if there was subtraction here, then the sigma would distribute over subtraction. So this is two properties kind of merged together here. And the proof would be really similar, just instead of a plus here, you'd have minus, and then the negative would factor out, and you'd end up with a negative there. So, so here we go. You get to memorize this one. Basically, sigma distributes over addition and subtraction, which makes it special because very few things in math do distribute over addition and subtraction. Okay, another property that you are going to find helpful to be familiar with here, property 2. The sum as I goes from 1 to n of a constant times a sub I. So in this case, and if you recall, you can factor the constant out in front. There we go. And you could prove this one as well. It's as easy a proof as this one, but I think that for time purposes, and so it's not too repetitive, I'll figure if I proved that one, it's probably good enough. Okay, just a little practice for you. Example 1. Okay, before you do example 1, even if it means pausing the video, I really recommend that you, I really recommend that you memorize the properties or do your best to re-memorize those. I know you had them memorized at one time. Okay, so the directions are for you to evaluate each sum. Part A would be the sum as I goes from 1 to 200 of I. Okay, so in this case, we would be utilizing this formula right here. Just your n value is 200. So you'll see me do 200 times 201 divided by 2. Which would be, cancel the 200 and the 2, so you'd have 100 times 201. So your answer would be 201 with 2 zeros after it. So 20,100. Okay, part B. The sum as I goes from 1 to 14 of negative 10. So in this case, you've just got a constant here. You do start at 1, so you would just have 14 negative 10s. So your answer would be negative 140. Okay. Part C, let's do the sum as I goes from 1 to 7 of I squared. So this time, you would be using this formula right here. Just your upper bound is a 7. So you'll have 7 times 7 plus 1 or 8. 2 times 7 plus 1 is 15, and then over 6. So you'll see 7 times 8 times 15 all over 6. Okay, please practice the art of canceling before you multiply. So like the 6, for example, can cancel with the 8. Now you have a 4 and a 3, and then the 3 can cancel with the 15, and now you have a 5. So you'd really just need to multiply. Let's do this. 4 times 5, which is 20, and then times the remaining 7. So your answer, my friends, would be 140. Okay, part D. Let's have you do the sum as I goes from 1 to 20 of the quantity 10I squared minus 1. So for this problem, you can see the rule in here does not look like any of these properties 1 through 4. So you'll need to use some of the properties of sums here in order to get the green light to use the other properties. So in this case, whether you show it in this many steps or not, this is kind of what should happen in your head. So you could distribute, first of all, you could distribute sigma over subtraction. So you'd have the sum as I goes from 1 to 20 of 10I squared, and then minus the sum as I goes from 1 to 20 of 1. And then from there, this almost looks like the third property that we listed and the property that I just used in part C, but the 10 makes it so that technically it's not, but you can use the constant multiple rule for sums and factor the 10 out. So you'd have 10 times the sum as I goes from 1 to 20 of I squared, and then minus the sum as I goes from 1 to 20 of 1. So now from here, now this is something that you could use that third property on. So now you can replace this whole sigma expression. So I'll bring the 10 down, and we're going to multiply it by, notice you don't write sigma anymore because we are adding it up already. So you'd have 20 times 21, and then 2 times 20 plus 1 is 41. And then all over 6 for that piece right there. Okay, and then minus, and then here 1 is just a constant, so you'd have 21s, also known as 20. Okay, so now let's practice the art of canceling before we multiply. So the 6 can cancel with the 20, and then we'd have a 3 here, and we'd have a 10 here. And then the 3 can cancel with the 21, so we'd have a 1 here, and we'd have a 7 here. So really, we just need to figure out in whatever order makes sense to you. I kind of like doing 7 times 41, because what would that be? 287, I think. And then you multiply by 10 So let's see. So we'd have, oh yeah, and then the other 10. Okay, so we'd have 287, but then times 10, but then times this 10 as well, and then minus the 20. So the final answer here would be 28,680. Like so. Okay. All right, my friends, one more example, and then we are done with this section. All right, example 2. So let's see. Okay, evaluate. Each sum. Part A, the sum as I goes from 1 to 10 of I plus 1 over 10. Part B, the sum as I goes from 1 to 100 of I plus 1 over, whoopsie, typo, sorry, back here, instead of 10, it's 10 squared. And then I plus 1 over 100 squared. And then part C, let's do the sum as I goes from 1 to 1,000 of I plus 1 over 1,000 squared. Okay, for this problem, if we were in class, I would give everybody time to kind of brainstorm on it and maybe even have you work in partners. And here's what you would find out. You'd find out that these 3 problems are very repetitive. Every single one basically has the same rule. They just have a different number here for the upper bound, and that number matches your denominator that's getting squared, the base of your denominator down here. So otherwise, the rule is exactly the same. And so you'd basically find that you did a very repetitive thing for all 3 parts. And each thing was kind of time consuming. So for the purpose of the video, I'm not going to drag you through the mud like that. So that's one nice thing about online learning. Anyway, so what I'm going to do is show you a trick for how to handle this. And then it's something that we're going to need for where we're going with all this anyway. So what we're going to do is we're going to generalize the situation that's going on here. So every single one of these problems is a sum as I starts at 1 for starters. And then the thing that's different is this upper bound. So I'm just going to put n to represent the upper bound. And then every single one had I plus 1 as the numerator. And then every single one had your upper bound getting squared as the denominator. So what that means is that if I call the upper bound n, then I would need to write n squared as the denominator. Okay, so in this case then, if I was to what I'm going to try to do is try to get a rule for this in terms of the upper bound. So I'm trying to get this to be all in terms of n, my upper bound. So for starters, I'm going to use what's called the constant multiple rule. Now listen to this very carefully because this is logic that we use for a long time, not just in this context, but others like next year. As far as this sum is concerned, think about what's the variable. What changes value every time if you were to expand this out? And the answer is I. I goes from 1 to 2 to 3 and so on, and then n is just where it stops. So as far as sigma is concerned, I is the variable, n is a constant. So in that case, you can actually use the constant multiple rule for sums and rewrite this as 1 over n squared times the sum as I goes from 1 to n of I plus 1. Now I know 1 over n squared is not actually a constant, but as far as sigma is concerned, I is the thing that changes value, and so therefore n is a constant as far as sigma is concerned. Okay, Now you can use the sum rule for sums to distribute sigma over this addition that you see here. When you do so, make sure 1 over n squared is multiplied by the whole quantity. So we'd end up with 1 over n squared times the quantity. The sum as I goes from 1 to n of I plus the sum as I goes from 1 to n of 1. Now, our whole goal was to get a rule in terms of n, so that means we need to get rid of all sigma expressions and all functions of I. So we're about to do that because we have the green light now to use one of our formulas that we memorized, I think formula number 2 that you should have memorized here. So what can I replace this sum here? The sum as I goes from 1 to n of I. Well, I could replace it with n times n plus 1 over 2. I'm going to put those parentheses there, sorry. And then what could I replace the sum as I goes from 1 to n of I of 1 with? Well, you would have n ones, also known as n. There we go. And the truth is I could leave it like this, but the person we're simplifying for later is ourselves. So I actually think it would pay off kind of 3 times if we were to just simplify this now. So, so let's start by maybe getting common denominator in here. So we could accomplish that by multiplying n by like 2 over 2, for example. And so what would we then have? We'd have 1 over n squared times, I'm going to go ahead and distribute this in. So n squared plus n plus, and then you'd have 2n all over 2n. And then notice we have some like terms here. So n plus 2n is 3n. So we'd have n squared plus 3n over 2n, like so. Okay. And then you could, now that I've got this simplified, you could always refactor this and cancel one of the n's out. So let's say we did that. So I'd have n times n plus 3 all over, I don't know, whatever, n squared times 2n. And then these n's could cancel out or divide out and be 1. So then you'd have n plus 3 over 2n squared. There we go. Okay, so that was a ton of symbol pushing, but I'm going to go ahead. Notice the way that I aligned this problem. So I had what I'm finding, and then as I worked, I went straight down. So I'm going to bring my prompt down and line it up with what I found. So what is this for? This is for if you have this sum that's of the form I going from 1 to some upper bound of I plus 1 over your upper bound squared, here's a little rule for it. And how can that help me out? Well, instead of doing basically this 3 times over, I just did it once, and then I have a little rule for it. Whatever your upper bound is in this exact situation, you just add 3 to it, and then divide by that number squared and doubled. So up here, you'd end up with 10 plus 3 over 2 times 10 squared. Like so. And so what would we have then? We'd have 13 over 100 times 2, 200. I feel like I've made a mistake. I feel like we should just get 20 down there. What did I do? Oh, here's what I did. You guys have probably been dying this whole time. The denominator here would be not 2n, it would be 2. Sorry, guys. And then just 2 here as well. And then you wouldn't cancel that, you'd just cancel one of these back here. There we go. Okay, so the rule is not n plus 3 over 2n squared, it's n plus 3 over 2n. Sorry, everybody. So then up here, that you wouldn't have that square there. Okay, there we go. So you'd have 13 over 20. There we go, that's what I was expecting. There we go, 13 over 20, okay. Okay, and then I plus 1, so this one right here, it's this exact situation, you just have a 100, so you'd have 100 plus 3 over 2 times 100. There we go. So that would be 103 over 200. Okay, and then this one, you would have 1,000 plus 3 over 2 times 1,000. There we go. Okay, all right. Okay, one more problem to think about. And I'm going to put it right here, I think. Am I going to put it, can I fit it right here? Yes, I can. Okay, part D. Let's say I asked you, what is the limit as n approaches infinity of the sum as I goes from 1 to n, and then I'm going to use the same exact rule of I plus 1 over n squared. So there are two ways to figure out the answer. You could look at the trend as this number right here got bigger and bigger in magnitude. You could look at the numbers that we got. So we had 13 over 20 when n was a 10. When n was a 100, we had 103 over 200. And when n was 1,000, we had 1,003 over 2,000. And you could figure out what does it look like these fractions are approaching in value as this upper bound gets larger and larger in magnitude. And I think a lot of people, based on that type of thinking, would say 1/2. And you would be exactly right. So now, let me make my infinity look a little more like infinity. There we go. Anyway, so in the next example, and the last example for this part 1 video, we're going to show how could you figure out this answer without having to do this type of thinking. So example 3. Let's have you evaluate. And part A is going to be recycled. It's going to be a little repetitive, but it should help you get a feel for the flow of handling all the notation. So I'm actually going to have you redo the limit as n approaches infinity of the sum as I goes from 1 to n of I plus 1 over n squared. And we're going to show how to handle this as if you hadn't done example 2 before. How to handle all the notation and all that fun stuff. Okay? So for something like this, you're going to work from the inside out. So you're first going to try to get this sum to be in terms of n, which I know we already did, my friends, we already did. But this is showing you how to handle it with the additional notation with a limit in front. Okay, so first goal, get the sum to be all in terms of n, and then the second goal is to, or to get the sum, replace the sum, I should say, for a rule in terms of the upper bound, and then after that, we're going to take the limit value. Okay, so with that said, we are going to, every time you're going to need to write this limit expression until you finally do let n approach infinity. So you'll carry this notation with you. In order to get this closer to have a rule in terms of n, you're going to do exactly what we already did. So you're going to factor out the constant multiple. Now, as far as sigma is concerned, I is the variable, so 1 over n squared is a constant. But as far as the limit's concerned, n is the variable, because n is changing and approaching infinity. So you can factor 1 over n squared out right in front of sigma, but do not factor it in front of the limit. That would not make any sense. So this is how you'd carry all this notation around. The next thing that you will do, carry your limit as n approaches infinity down. And then you're going to distribute sigma. Notice the bracket. It's so that 1 over n squared gets multiplied by everything like it was supposed to back here, even though I'm expanding the sum. Like so. Okay, next step, bring down the limit as n approaches infinity of 1 over n squared times the quantity. Now we can replace each sum expression with the proper rule in terms of the upper bound. There's the rule for this one, and then the rule for the second sum would just be n. Okay. Next, I think I'm going to try to show you some minimalist work because this can get really kind of laborious otherwise. I think that, trying to think what the fastest way to do this is. Probably either distribute that in. Do I like that for this one? I really do. No, let's stay textbook. Let's do, no, it's faster. Let's distribute 1 over n squared in. So we're going to distribute like this. Okay. And what I'm going to do here is I'm going to show you when we do this, how to kind of what matters and what doesn't. So, for example, this is what we get when we multiply that in without worrying about anything canceling out. And then you would distribute it into the n, so you'd end up with this. And I think a lot of people, when you look at what I have here, you're like, my God, lady, just cancel the n's. But I want to show you that it kind of won't matter whether you do or not. So if you recall properties of limits, limits distribute over addition. So either on paper or in your head, really what I'm needing to figure out is what's the limit as n goes to infinity of this first part, which you could think of as n squared plus n over 2n squared, plus what's the limit as n goes to infinity of the second part. Now this step that I'm writing right here is something that I usually just hold in my head, but I'm just kind of showing you what's in my head. And then now, now without canceling anything down, I want you guys to recall infinite limits like this and horizontal asymptotes have something in common. So basically what this first part is asking is, hey, if you were to graph this function, what's the end behavior? And so if you look, the degree of the numerator is 2, the degree of the denominator is 2, and the leading coefficient at the top is 1, the leading coefficient at the bottom is 2. So the answer to this first limit would be 1/2. And if I taught section 11.4 correctly, I was trying to show you that you could use horizontal asymptote rules that you've known since Algebra 2 interchangeably with doing all the work that I showed for those. Same here, horizontal asymptote and behavior. So what's the degree of the top? 1. What's the degree of the bottom? 2. What was the horizontal asymptote on something in that situation? It was 0. There you go. So your final answer would be 1/2, which is what we got doing a slightly different type of thinking in example 2. Okay, same directions, just evaluate. Let's give you one that you didn't already beat to death in a previous example. So part B, let's give you the limit as n approaches infinity of the sum as I goes from 1 to n of 5i squared over n cubed. This would be a really good one to pause the video and see if you can get the answer on your own. The answer to this one should be 5/3. So go ahead and work it out and see if you can get that, and then come back to me and play the video, and we can check and see if we do this the same way. You can check your notation and all that. But this is how I'd go about it. So you'd have the limit as n approaches infinity. You'd use the constant multiple rule and factor out 1 over n cubed in front of sigma, but not in front of the limit. And actually, you know what? When I'm at it, I'm going to factor the 5 out as well. Sorry, my hands don't work very well. I've had my hands in a splint for quite a few days, and I kind of lose some coordination and range of motion and all sorts of stuff. Okay, there we go. So if I factor out 5 over n cubed in front of sigma, then I just have I squared left. Now I'm going to replace the entire sigma expression with the appropriate rule in terms of the upper bound, n. Okay, Now, in the spirit of these problems being hard enough without doing a necessary algebra, I want to teach you a kind of a trick for how to not need to expand this garbage out. So here's what I'm going to do. I'm going to pretend that I multiplied the top all together, and I'm going to ask you, what would the highest power of n be if you multiplied all this garbage out up here? And the answer is 3. So your numerator is degree 3. Your denominator is even easier to figure out. It's also of degree 3. So the numerator and denominator have the same degree. So, and this is asking for horizontal asymptote or end behavior. So it will have a horizontal asymptote. Now we just need to figure out what the leading coefficient would be if you multiplied it out. So if you multiply the top out, I claim that the leading coefficient would just be basically 5 times 1 times 1 times 2. So the leading coefficient on the top would be 10, and then the leading coefficient on the bottom would be 6. So your answer, my friends, would be 10 over 6, which reduces to be 5/3. There we go. All right, my friends, that's the end of section 11.5, part 1, which is a review and kind of an extension from certain summation formulas that you've had in the past. I hope this makes sense, and I hope you guys will reach out and ask me questions if things don't. Take care, everybody.